Hello everyone, welcome back to 3 Deviations. In today's video we want to talk about absolute extrema. So what do I mean by an absolute extrema? I mean that I am talking about the absolute maximum and the absolute minimum of a function. So in single variable calculus, what we could do is if I had a graph like this, maybe, and here's my x-axis and there's my y-axis, and I wanted to find the absolute maximum or the absolute minimum on this interval right here. So if I want to find this interval, the absolute maximum, the absolute minimum of this, right? Now, one of the things that we learned is that I can set the derivative of the function. I can set that equal to 0 and solve for x. And that will give me where my tangent line is equal to 0. So that would be one candidate. But that is a local maximum, and this here is a local minimum. But as you can see, our graph gets a lot higher and it gets a lot lower on our interval. So this would not be our absolute minimum, and this would not be our absolute maximum. This would be our absolute minimum, and this would be our absolute maximum. Okay, so that's important because we need to be careful about checking our boundary conditions, because our boundary conditions often include the absolute extrema, whereas the local extrema will usually be where a derivative equals 0. So this is actually quite a tedious topic, not because of any multivariable calculus trickery that we need to use, but more so because of the algebra and single variable calculus that it requires in order to solve. So these problems are quite tedious, they just take a long time. So let's get into it. Anyways, we would like to begin by talking about the extreme value theorem for functions of two variables. So let's say that f of x, y is continuous on a closed bounded set D. Now when I say closed and bounded, closed means that the set is closed, right? So it is a closed shape. I can color it in and it looks like a shape, a triangle or what have you. Then when I say bounded, I mean that it has a boundary. This has a boundary, a circle has a boundary. If I had a circle that was like this, but it wasn't defined here, then that would not be closed because I could go in or out through there, right? So it needs to be closed and it needs to be bounded, okay? And that also means that this boundary is a part of the set. So in that case, we can say definitively that f has a maximum at some point x1, y1, and f has some absolute minimum at some x2, y2. So in order to find the values of our absolute maxima and minima, we need to find the values of the critical points. That will give us candidates for anything that is not in the boundary that might be our absolute maximum or minimum candidate. Then we need to find the extreme values on the boundary of D. So in order to do that, you have some boundary. So usually this will be a rectangle. If it's not a rectangle, then you need to do some more crazy parameterizations and whatnot in order to help you out. But anyways, what you would do is I would check in here, I would check inside of D to see if there are any absolute maxima or minima in there. If not, I would check each of these boundaries separately. So this would be a function of y, because this would be projected as some function, as some height above here, above this line as a function of y. I would check for absolute maxima and minima on that line, because that would be a candidate. And of course that sets x equal to some constant, because the constant would be there. And then I would try the same for this line to see if there are any absolute maxima or minima. Then I would check this line to see if there are any absolute maxima or minima, and then I would check this line to check if there are any absolute maxima or minima. All right, so let's try an example for this. And of course, after you do that, you compare results to see if the values of the critical points are higher than the values of the extreme values on the boundary of D. Okay, here's an example. I've just showed the whole thing out because you can go at your own pace, but anyways, let's say that I have the function f of xy equals x squared minus 2xy plus 2y on the domain D such that ordered pairs x and y are governed by x being between 0 and 3 and y being between 0 and 2. So we can draw what this looks like. So if I have my xy plane, so here's my xy plane, and here's my point. So x is between 0 and 3, so there's 0, there's 3. Y is between 0 and 2, there's 0, there's 2. So we are on this kind of domain here, right? So this is our domain, and z goes out of the blackboard. So the function lies above this domain, d. Okay, so what we do first is we find our partial derivatives, and we set them equal to 0. So if I set partial x, if I take the partial derivative with respect to x of the function, I get 2x minus 2y equals 0. Then if I do the same for y, I get negative 2x plus 2 equals 0. Now I can solve for x from this second equation for partial y of f, and I get x equals 1. And now, of course, from this equation, you can see that x and y must be the same for them to equal 0. So we get 1 comma 1 as our extreme value for inside of our domain. But now we need to check the value of that. So we plug it into the function. We get f of 1 comma 1 is equal to 1. Well, now we've only done half of the work, or really less than half of the work, because now we need to find all of the values of our possible values on our boundaries. So first, we are going to try the boundary where x is equal to, or where we have we're going along the line y equals 0. So we're going along this boundary first. This is any value of x along this line between 0 and 3. If we, and this of course means that y is equal to 0. So if we plug that into our function becomes x squared. And we're evaluating between 0 and 3. So we want to find the minimum and the maximum here. So x squared is always increasing. So x is between 0 and 3. So the minimum value that this function can take is 0, and the maximum that this function can take is 3 squared, which is 9. So we found our minimum and we found our maximum for this leg. Now we find it for the next leg. So we're going to find it for this leg here. So now we set y equal to 2, and x can go between 0 and 3. When we plug this into our function, we get x squared minus 4x plus 4. Now, in order to find the maxima and minima of this function on this interval, we need to take its derivative with respect to x, and then we can set that equal to 0. So this is like finding your critical values in single variable calculus. And from here we find that the minimum is going to be equal to 0, and the maximum is going to be equal to 4 on this interval. Finally, we have a couple more. So now if I'm taking y along x equals 0, so this part of the domain, I get that my function will become 2y, because of course we don't have any x contributions. And now we're going between 0 and 2 for our y values. And so here you can obviously see plugging in directly. Your minimum value is going to be 0, and your maximum value is going to be 4. Now, finally, what we have is this final leg of our domain boundary, which is y, or going along x equals 3. So we take f of 3 comma y equals 9 minus 4y, plugging into our function, and that's between 0 and 2, again solving using your optimization and what have you, or solving for the boundary conditions. We have that the minimum is equal to 1 and the maximum is equal to 9. So we have all of our values, so we just need to find the lowest minimum and the highest maximum. This one's obviously out. This one is out. This one and this one are out. But now we've got these zeros and we've got these 9s. So the zeros are going to be the lowest values and the 9s are going to be the highest values. So our absolute minimum on this interval is 0 and the absolute maximum is 9. Now where does this take place? So we can obviously plug that back into the domain. Okay, so thanks for watching. In today's video, we would like to discuss the Lagrange multipliers and constrained optimization. So we will look at that in the next video. That will be our last topic for Unit 3. Then we'll be ready to move on to some volume integrals. All right, thanks for watching. See you next time.